So here's our presentation on the new concept for a thermal management system in a lithium-ion battery using air cooling and heat pipes for electric vehicles.
My name is Matthew Warner.
My name is Ryan Wirt.
And I'm Peter Woodruff.
So to start off with, we're going to have our why, how, and conclusion section. Then we're going to go into the two different types of ANSYS modeling and finish up with our MATLAB code. The division of responsibilities was myself, Ryan Wirt, and Peter Woodruff on the ANSYS modeling, and Matthew Warner was handling the MATLAB coding. So for our why, how, and conclusion, our why was to design an improved electric vehicle motor that improved battery life, power, and safety. And then we did that by using heat pipes to reduce the temperature inside of the battery module. And our conclusion was that heat pipes outperform both natural and forced convection in terms of cooling ability. For forced convection, we used air at 2 meters per second with a 15-degree ambient temperature. And for the battery walls, they were set to an initial temperature of 50 degrees Celsius. So on the graph that is seen to the right hand of the slide, we can see what is the temperature in the left margin and the time in the bottom. And what this demonstrates is how the temperature of the battery with forced air convection will rise to approximately 44 degrees Celsius before over time cooling to 50 or to 39 degrees Celsius.
So I was in charge of running the simulations for the heat pipe in our system. So for our heat pipe, for the evaporator, that's set to 500 degrees Kelvin, and the condenser is set to around 300 degrees Kelvin for our experiments. Next slide. So I ran a number of iterations to determine the mesh independence of our experiment. We can see the results on the table there. You would expect the temperature to go in a single direction as the number of elements increases or decreases, but we didn't see that in this experiment here. Next slide. We also looked at the temperature at a single point in the one simulation. So the temperature continued to change as time was changing. You'd expect the temperature to continue to increase as time went on, but that didn't happen. And I'll explain why I think that is in a second. Next slide, please. So we also looked at the heat flux at a particular point. You can see in the figure that that point is right in the center of the evaporator there. And the table shows that the heat flux changes as the time increases. For that, you would expect the heat flux to either increase or stay the same. But as you can see on the graph, it fluctuated quite rapidly. And I'll explain why I think that is on the next slide. Next slide. Yeah. So I think the reasons why we got such large discrepancies in heat flux and temperature could have been for a number of different reasons. So I think there's a wide range of heat flux and temperature ranges because of the fact of the boiling water. So you can see on the two pictures there that the steam bubbles actually move a lot, even in the time between the 0.5 second image and the 0.75 second image. And because of that, there will be a wide range of heat flux and temperature for both those points there. So yeah, depending on these steam bubbles, the temperature and the heat flux will be higher or lower. So it's not just dependent on increasing or decreasing time that the heat flux and the temperature are going to increase or decrease. Next slide.
Okay, so for the MATLAB coding, we used 3 different wick structures to show us the heat transfer rate as well as the boiling limit. The 3 wick structures used was a wrapped screen, which is illustrated in equation 1, the packed sphere, which is equation 2, and sintered fiber, which is equation 3. Now, all of these wick structures were used with different porosity values to gain a sense of how the heat transfer rate would react at a certain temperature. The resistance totals, equation 4, equation 5, and equation 6, which is the heat transfer rate and the boiling limit, were used from the thermal design book. Next slide. So for the heat transfer rate, the desired outlet temperature was 37.5 degrees, and the goal was to have the heat transfer in between 30 to 35 watts. That was a published value that we tried aiming for. And as you can see, the horizontal axis, which is the porosity, changed the heat transfer rate. And so the lower porosity on the wrap screen was the best to get around 30 watts. Next slide. Now for the boiling limit, the evaporator heat flux would be high enough to where boiling occurs in the wick. So we need to know what the limit is for that. And for the boiling limit, the value decreases as the porosity increases. So the wrap screen again would be the best option to get close to 30 to 35 watts. Next slide. And these are our references used. Thank you.